Hello, good people, and let's begin with the first episode of Prime Puzzles. The first set given was Andrew plays a new variation of the poker game with his friends Bob, Charles, and David. The rules of the game are as follows. There are 10 rounds in the competition. Each player has to bet coins equal to the round number. So in every round, whatever is the round number, each person is betting 10 coins. Okay. That is, each person bets one coin in the first round, 2 coins in the second round, and so on. The player who wins the round gets all the coins bet by all the 4 players, while the remaining 3 players lose the coins they bet in the round. Okay. So in any round, let's say we are looking at Charles. In round 3, he will only have 2 possible outcomes. Either he will lose the 3 coins he has bet, or he will win 9 coins from other players. Either he will lose the 3 coins that he has bet, or he will win 9 coins. Or can I say the two outcomes are minus n, or the win is 3n. Other participants apart from A, B, C, D. For Charles, round 3, A, B, C would have bet 3 coins each themselves. So if those people give 3 coins, he ends up winning 9. If he loses, he ends up getting -3. So in every round, that is how this Charles would be operating, or any participant would be operating. Charles is here is just an example. Okay. The person with the maximum number of coins at the end of all the rounds of the tournament is declared as the winner of the tournament. Okay, whoever wins maximum number of, or whoever has the maximum number of coins. See, the difference in the statement is winning maximum number of coins. If I start off at as 1 million coins, if I start off at 1 million coins, the maximum coins anyone can win, if he wins all 10 rounds, that person will only win 165 coins. And if that person is starting off at, let's say, 500 coins, he ends up winning 165 more. He'll still end up with 665 coins. Uh, I started off at how much? At 1 million. So I would still have more coins than that person. So the person with the maximum number of coins at the end of all the rounds of the tournament is declared as the winner of the tournament is not the same as the person who wins the maximum number of coins in the tournament. There is a difference. Okay. Each player started the first round with a certain number of coins. In each subsequent round, players bet only from the coins left with them after betting on the previous rounds and or winning the previous round. It is known that each player was left with enough coins at the beginning of each round required to bet on that round. Okay. Everybody always had adequate number of coins available with them to bet in that particular round. So if we have reached round 7, the lowest number of coins somebody would have available with them will be 7, so that they can bet 7. Okay. First question. Suppose Andrew starts with a single coin that he bets in the first round. What can be the maximum number of coins with him at the end of the 8th round? Okay. Andrew is starting off at 1. Now in round 1, if we are looking for a maximum number of coins with him at the end of the 8th round, basically what we want is in every round Andrew has won so far. In round 1, maximum he can win is 3n. So he will get 3 coins. At the end of round 2, he will get 6 coins, 2 from all other 3 participants. In round 3, he'll get 9. In round 4, he'll get 12. In round 5, he'll get 15. In round 6, he'll get 18. In round 7, he'll get 21. And similarly, 24 at the end of round 8. Okay, let's add these up. This is an AP. So 3 plus 24 is 27, 8 terms. So 27 into 4 plus this extra 1 that we have. Altogether, we should get our answer as 109, which is also present in the options. So yes, our work is done. Our entire understanding or operation here is based on the simple idea, this. In every round, you will either win 3n or you will lose n. So if we want the maximum number of coins, let him win 3n every time. Okay, next. If a bonus equal to the square of the round number, That is bonus of 1 coin for first round and bonus of 4 coins for the second round, and so on is given to the winner of the round over and above the number of coins won for that round. Then what can be Bob's maximum score at the end of 8 rounds? Okay. Seems similar to the last one, but there are additional conditions. It is known that he loses 2 rounds till that stage, third round being one among them, and wins the remaining 6 rounds. He also starts with 3 coins, out of which he bets 1 coin in the first round. Okay, he starts off with 3 coins, and then we need a maximum number of coins with him at the end of 8 rounds. Sorry, round 2, 3, round 4, round 5, round 6, round 7, round 8. Because we want to maximize the number of coins that Bob ends up with, and he's supposed to lose 2 rounds, one of them being round 3. So he would have lost 3 coins here. He would have lost 3 coins here. Which other round should he be losing? Of course, round 1, because that is where he's betting the minimum. So he will lose also minimum. In all other rounds, he should be winning. In round 1, he should be losing. So he goes -1 here. He wins 6 here. 3 and he will win. And there is also a bonus of the square. So there is a +4 here. Here he will win a 12 and a 16, a 15 and a 25, an 18 and a 36, a 21 and a 49, a 24 and a 64. All we have to do is simply add these numbers up. Even while adding these numbers up, the first thing I can see is I can straight away take this -4, -3, -1 away. Okay. I get 88 and 70 and 54 and 40 and 28, and these two add up to give me a 9. Okay. I can happily see that my unit digit is going to be 9 among the available options. We have 2 options which have unit digit as 9, but when you look at these 2 numbers, clearly you know your answer cannot be 109. So it should be 1. But for peace of mind, if you want, we can also go ahead and add these up. 9 plus 28 is 37, 37 plus 40 77, 77 plus 54 is 131, 131 plus 70 is 201, 201 plus 88 is 289. Simply, if you can catch on to this -n and +3, life becomes simpler. Let's look at the other 2 questions in the set. What can be the maximum number of coins Charles must start the tournament with so that he has enough coins to bet in all the rounds of the tournament? It is known that he loses all the prime numbered rounds and wins all other rounds. Okay. He loses all the prime numbered rounds. So round 1, round 2, round 3, round 4, round 5, round 6, round 7, round 8, round 9, round 10. About Charles, I don't know what his initial number of coins are, but he wins round 1 because he only loses prime numbered rounds. So he wins round 1. He gets 3 coins here. Here he loses 2 coins. Here he loses 3 coins. Here he wins 4 coins. Here he loses 5 coins. Very sorry, I have made a terrible mistake. Here he will win 12 points. Here he will win 12 points. Here he will win 18 points. Here he will lose 7 points. Here he will gain 24 coins, 27 coins, and 30 coins. We know precisely what his outcomes are going to be. Now, we need to find out the minimum number of coins that he starts the tournament with so that he has enough coins to bet in all the rounds of the tournament. So now here, don't try to make an equation out of it and then solve. Simply work with the options that are available. Let's start with 4. If he started off with 4, here he has 7, so he can bet 2. He has 5, so he's left with 2. In round 4, does he have 4 coins available to bet? No, not available. Therefore, 4 cannot be the answer. We started off with the smallest option. Let's go with the other one, the next smallest option now, and check. Until the time we find the right number, we keep checking. Let's say he started off with 6. He ends up with 9 coins here, loses 2, reaches 7 coins here, loses 3, reaches 4 coins here, 16, loses 5, reaches 11 coins here. He has 6 available. In fact, he's got 18 more, so 29, loses 7, 22, and after this, he keeps on winning only. So if he started off with 6 coins, his life would be simple. He would be able to accomplish every goal that he has, being able to bet adequate number of coins in each round. So the answer to the question should be option 2, 6. Pay attention, we are not solving for the smallest number. We are simply trying to identify the best option among the ones that are available. Okay, let's look at the last question. David starts the tournament with 55 coins, out of which he bets 1 coin in the first round. Now see, this 55 is also a fun number. 55 is sum of first 10 natural numbers, out of which he bets 1 coin in the first round. It is known that he had more than 55 coins at the end of the 10th round of the tournament. He had more than 55 coins at the end of the 10th round of the tournament. Which of the following can be the difference between the number of coins he starts the tournament with and the number of coins that he had at the end of the 10th round of the tournament? Now, it would have been perfectly all right if you skipped this question, but then this fact, coupled with the fact that these numbers that you see here are nothing but remainders with 4, can possibly lead you to a smart way of viewing this question. So right now, let's say he loses all rounds. Loses all rounds from 1 to 10. So in every round, if he lost, he would be left with 0 coins at the end. He started off with 55 coins. If he loses all rounds, he's left with 0 coins. Yes. Now, if he had won round 1, how many coins will he gain now? How many coins will he gain now? I'm stepping away from this setup a little bit. There, we did not know whether he has. What we are trying to do here is, previously you are betting and then you are either winning or losing. Here, we have made sure that he's lost all matches. He's lost all matches. So now for every round that I turn to a win, let's say he ended up winning round 1 instead of losing. Previously, he is getting a -1. Now, if he wins round 1, the net changes of 4. Similarly, let's say he lost round 2 earlier and now he ends up winning round 2. The net changes of 8. For every round 1, if it turns from a loss to a win, his score goes up by 4. If it turns from a loss to a win in round 2, his score goes up by 8. If it turns from a loss to a win in round 3, his score from -3 will go to +9, or a net change of 12. And so on. You can go ahead and list down all numbers. Not that you need to, but you can go ahead and list all numbers, because by now the smart thing should be identified. 32, 36, where have we got? Okay. And finally 40. We had started off by assuming he loses all rounds, which we know is not true. He's ended up with more coins than what he had started with. So he's definitely not done that. But can you see, anytime you convert a loss to a win, anytime for any round, when you convert a loss to a win, his score will increase in multiples of 4. After all the losses that we had handed him, he was at 0 coins. But anytime a loss turns to a win, his score increases by a multiple of 4. So his final score from 0, if it has increased by a multiple of 4, can I say it will finally be a multiple of 4? It will finally be a multiple of 4. And what we finally needed was difference between the number of points he starts the tournament with, which is told to us as 55, and the number of points he has at the end of the 10th round of the tournament. So 4n minus 55. 4n minus 55. Can it be equal to 0? Not possible. Can it be equal to 2? Not possible. Can this be equal to 3? Not possible. Can this be equal to 1? Yes, this is the only possibility that you have. In fact, if you want to go ahead and see which possibility, simply make him win round 5 and round 9. That should be enough. He wins 56 points. He wins 56 points. At the end of the tournament, he has 56 points available. He's happy, but then that was not the concern. The fact that the total number of coins that he will have at the end will necessarily be a multiple of 4. That is the key learning or key insight that enables us to solve question 4. This is prime example of when, even if you manage to solve 1, 2, and 3 with a certain setup, if 4th requires an additional bit of thinking, even if you can't reach the precise answer for 4, you can happily move away from it, not a problem. You don't need to solve all questions within the set. Let us look at the second set now. Donald, Barack, George, and Bill are playing a game. In the game, initially they place a number of identical chocolates, not more than 12 on a table. Initially, Donald has his turn, followed by Barack, George, and Bill in that order. Each participant picks up either 1 or 2 or 3 gold chocolates in his turn. After Bill has picked up 1 or 2 or 3 chocolates, if any chocolates are remaining, the game continues with Donald, Barack, George, and Bill having their turns in that order again. So basically a cycle. The game stops when the last chocolate has been picked up. Okay. This is an advanced version of coin picking. Coin picking is a setup, but within this coin picking itself, the fun thing is usually coin picking sets have 2 people or at max 3 people. This set has 4 people, which has its own unique challenges. The participant who picks up the last chocolate gets 3 points. The participant who comes immediately next in order gets 2 points. And the participant who comes immediately next to the participant who gets 2 points gets 1 point. The remaining participant does not get any point. For example, if George picks up the last chocolate, he gets 3. Bill gets, while Bill, Donald, and Barack get 2, 1, 0. 2, 1, 0. So basically, if you're a smart player, you would not want your immediate neighbor to win. The person right after you, he should not win. If you can delay his victory, that will be your ultimate strategy. If you can delay his victory, that will be your ultimate strategy. Either you pick up, you have 3 or less than 3 coins available, coins or chocolates available in front of you, or if you have more, at least ensure the next person does not have 3 or less chocolates available in front of them. We'll get to it shortly. The player who gets 3 points is declared as the winner. All the participants are rational and play in such a way to maximize their points. This is a very important instruction. If the question doesn't mention this, then this becomes extremely impossible to solve because then it is irrational. People can behave in any way, no? Okay. First question is, out of 12 different possibilities for the number of chocolates from 1 to 12, the winners for how many possibilities can be uniquely determined? So now, given that we were told that number of chocolates, identical chocolates were not more than 12, there are 12 distinct cases that are available for initial number of chocolates being 1 or 2 or 3 or 4 or 5, so on and so forth, up until 60. And within these, it is always, you can either think forwards or you can think backwards. You can think forwards or backwards. A lot of times backwards thinking is useful. Especially in 2-person games, it is always backward thinking that is useful. For 4 people game and very less number of chocolates, it could very well be forward thinking, is it? Let's see. Right now we are not solving, we are just reading through the question. Next is, if Barak wins all the 4 participants, if Barak wins and all the 4 participants get an opportunity to pick up chocolates, how many chocolates does George pick up? Okay. Barak wins. Okay, let's see. So we are going to try to solve those 2 questions with the logic or the information that is present in the set. Let's say if one coin was present initially, if one coin was or one chocolate was present initially, it should not be coins, it should be chocolates. In my head, coins, chocolates, that doesn't really make a difference. The objects are objects. Initial coins was 1. Okay. So Donald will pick that up. He gets 3 points. Barak gets 2 points. George gets 1 point. Bill gets 0 point. It is pretty unfair on Bill. He never had a chance to play, yet he ends up with 0 points. Can you see? That will be the same storyline, even if it is 1, 2, or 3, because every person can pick up 1, 2, or 3 chocolates in his turn. He'll end up winning. Barak will get 2, Barak will get 2, George will get 1, George will get 1, Bill will get 0, Bill will get 0. When it is 4 chocolates initially, then it is a problem. See, if it is 4 chocolates initially and you are Donald, you are the first person playing. If you pick up 1 chocolate, Barak will pick up 3. If you pick up 2 chocolates, Barak will pick up 2. If you pick up 3 chocolates, Barak will pick up 1. If there are 4 chocolates in front of you, if there are 4 chocolates in front of you, there is no way you can win. If there are 4 chocolates in front of you, there is no way you can win. In fact, it is guaranteed that the person next to you will win. If there are 4 chocolates in front of you, if you pick up 1, Donald picks up 1, Barak picks up 3. Donald picks up 2, Barak also picks up 2. Donald picks up 3, Barak picks up 1. Regardless of what Donald does, Barak will always win. Okay. So let's just take one setup where he picks up 1, he picks up 3. He ends up with 3 points. George will end up with 2 points. Bill will end up with 1 point. And poor Donald will end up with 0 points. There is no way Donald can change the outcome even in the slightest. With 4 chocolates, he's definitely losing. Okay. If there are 5 chocolates, now, if you are not winning, remember all the participants were supposed to be rational. If you are not winning, your target has to be the next person also does not win. If you are not winning, the next person should also not win. If Donald picks up 1, Barak has 4 chocolates left in front of him. If Donald picks up 1, Barak has 4 chocolates left in front of him. If Donald picks up 2, Barak has 3 chocolates left in front of him, and then Barak can win. So if Donald is rational and does not want Barak to pick up the last 3 chocolates off the board, what he will do is he'll pick up 1 chocolate, and now Barak will be left with 4 chocolates. Now see here, your processing should go like this. When Donald was faced with 4 chocolates, what did he do? He picked up 1 and George picked up 3. George ends up getting 3 points. Bill gets 2 points. Donald gets 1 point. Barak gets 0 point. There is nothing that Barak can do that will ensure that he does not end up getting, as in, there is nothing that Barak can do that will ensure he gets any points. If there are 4 chocolates in front of you, you are definitely a loser, your life is over. If there are 4 chocolates in front of you, you are definitely a loser, your life is over. There is nothing else that you can do. Okay. Let's say there were 6 chocolates available. If there are 6 chocolates available, Donald wants 4 chocolates in front of Barak, or Donald wants 5 chocolates in front of Barak. Think. If there are initially 6 chocolates available, if Donald brings 4 chocolates in front of Barak, then Donald ends up getting 1. But if Donald picks up if Donald provides Barack with 5 chocolates, he picks up just 1 chocolate. Let's say, or let me do it with different colors, maybe then it makes sense. Let's say Donald picks up 3, then Barack will end up picking 3 and Donald will have no points at all. That is, of course, not ideal. Donald doesn't want that. Let's say Donald picks up 2. If Donald picks up 2, now Barack has 4 left. So he'll pick up 1, he'll pick up 3. The points distribution will be like this. The alternate case would be, let's say Donald picks up 1. If Donald picks up 1, now Barack is faced with 5 chocolates. Now Barack has 5 chocolates in front of him. If he has 5 chocolates in front of him, go back. What did Donald do when he had 5 chocolates in front of him? He picked up 1. Then George will pick up 1. Then Bill will pick up 3. And then Bill will get 3 points. And Donald will get 2 points. Barack will get 1 point. And George will get 0 points. See, our critical decision maker here is Donald because he's the first person playing. He has 2 options. In one option, he ends up getting 1 point. In the other option, he ends up getting 2 points. Of course, Donald is going to prefer the latter option. He's going to pick up 1 chocolate and he's going to ensure that he ends up winning. He's going to pick up 1 chocolate and he's going to ensure that he's winning. Okay, so let's just get rid of these red symbols. Okay, wonderful. Now there are 7 chocolates. Very simply put, there is no way Barack is winning now. Donald doesn't really bother about Barack because even if he picks up 3, Barack picks up 3, then George will pick up the remaining 1 and he will win. There is no way Barack wins now. But Donald is not just thinking that way. Donald is thinking intelligently. What he's thinking is, if there were 6 chocolates left in front of me, the person who played right before me ended up getting 3 points. If there are 6 chocolates in front of me, what just happened? Oh my God. Okay, this is the problem. If there are 6 chocolates in front of me, Donald, if he's smart, there are 6 chocolates in front of me, the person who plays the move right before me ends up winning. So when he has 7 chocolates in front of him, what should he do? Should he not simply pick up 1 so that now Barack has 6 chocolates in front of him and the person prior to him, Donald, he will end up winning 3 points? If he picks up 1 chocolate, from the 7 that are present, Barack will have 6 left, and the same reasoning that we utilized for Donald will be the same reasoning that Barack will use to end up giving him the greatest chance of potentially winning. And then you have 3 here. This person gets 3 points, this person gets 2 points, this person gets 1 point, this person gets 0 point. And not just this, look at 8 coins. His target was, let's get 6 coins or 6 chocolates in front of Barack. This time he will pick up 2. And the storyline, again, Barack has 6 chocolates in front of him. So the behavior will be identical. Points distribution will also be identical. Even when it is dying, not a problem at all. Let me pick up 3 in the first round, 3 in the second round I will pick up. 1, 1, 1, 2 points, 1 point, and 0 point. It is fun. So far it is fun. This is the most difficult version that this will reach now. 10. At 10 coins. Can you see, if you reach 10 coins, what is the problem? If you reach 10 coins, what is the problem? If you pick up 1, or you pick up 2, or you pick up 3, If you pick up one or you pick up two. If you pick up one, Barack will end up with 9 points in front of him. If Donald picks up two, Barack will end up with 8 points in front of him. If you pick up three, Barack will end up with 7 points in front of him. And using the reasoning that we have, if there were 7 coins in front of Donald, he ended up winning. If there were 8 coins in front of Donald, he ended up winning. If there were 9 coins in front of Donald, he ended up winning. Regardless of what Donald does here, regardless of what Donald does here, Barack will definitely win. George will definitely come in second. Bill will definitely come in third. And Donald will definitely get zero. We don't even need to go through each of these movements. We don't even need to go through each of these movements. We know this is how the outcome has to play out. Moving on to 11. Moving on to 11. Now, if there are 11 chocolates in front of Donald, he knows if he ends up giving Barack 9, 8, or 7 chocolates, if he ends up giving Barack 9, 8, or 7 chocolates in front of him at the end, Barack is going to win, and he doesn't want Barack to win. So what will he do in his first move? He'll pick up one. Now Barack ends up with 10 chocolates in front of him. As soon as Barack has 10 chocolates in front of him, do we know the outcome, how it will get distributed? Most definitely. We don't even need to get into how many chocolates each person will pick up. As long as we were clear on what we did previously, every subsequent outcome is guaranteed. So let's go. If there are 10 chocolates here, this person will get 0, this person will get 3, this person will get 2, and this person will get 1. Following up, if there are 12 chocolates, now this person, if he picks up 3, Barack will have 9 chocolates left, which is not ideal. So there are two options for this person. They either pick up 2 and lead this person to 10, or they pick up 1 and lead this person to 11. They can either pick up 2. Where are we? Yes, we can either pick up 2 or lead Barack to 10 chocolates, or pick up 1 and lead Barack to 11 chocolates. Okay. So when Donald is deciding, see, if there were 10 chocolates in front of Barack, I end up getting 1 point. But when there are 11 chocolates in front of Barack, we haven't had that case, but we have had that case when there were 11 chocolates in front of Donald. When there were 11 chocolates in front of Donald, how many did the predecessor to Donald score? 2. So in this case, Donald is going to score 2. So which case will Donald prefer, picking up 2 or picking up 1? Of course, he'll prefer picking up 1. So what would happen is, Donald gets 2 points when it is 12 chocolates. Barack gets 1 point when it is 12 chocolates. George gets 0 points and Bill gets 3 points. Please, we don't have to get into the stupid picking up of what will this person do in this situation, that person will do in that situation. We have to simply build our reasoning up step by step based on what Donald was deciding. That is the same logic, because all of them are equally rational. All of them are using the same logic. So if Donald is winning at 1, 2, 3, when it is 4, Barack will win. Regardless of what Donald does, Barack will win. And Donald will then ensure that Barack does not end up with 1, 2, or 3 points in front of him. Then Donald will ensure Barack does not end up with 1, 2, or 3 points in front of him. This is a question that does not require a lot of mathematical manipulation, but it requires for you to think in backtracking terms. It requires you to put X person in Y's position and see how how Y reached his decision. So that is the same reasoning that X will also use. Once you have all this in place, let's get to individual questions. Out of the 12 different possibilities for the number of chocolates from 1 to 12, the winners for how many possibilities can be uniquely determined? Can you see we are able to uniquely determine for every round who won? If I can simply mark it, Donald, 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 Donald. Here it is Barack, here it is George, here it is Bill, Barack, George, Bill. We are able to uniquely identify winners in each of the rounds, therefore more than 10. If Bharat wins and all the four participants get an opportunity to pick up chocolates, how many chocolates did George pick up? If Bharat wins, so this is the game. This is the game. Okay. If Bharat wins, so what will happen? Bharat wins. How many chocolates did George pick up? Okay, wonderful. So 9, 8, or 7. 9, 8, or 7 is left. Regardless of whatever number of chocolates are left, he would want George to have 6 chocolates left in front of him. And when there are 6 chocolates left in front of you, you pick up 1 chocolate. So the answer here has to be 1. I don't care for how many Bill will pick up and then how many Donald will pick up and then how many. I did not know that there would be a question related to this, but regardless, can you understand the logic behind this? Whatever decision making Donald engaged in, even here, our decision making was 7 to 6, 8 to, sorry, 8 to 6 and 9 to 6. Every time we wanted to get the other person to 6, let us get the other person to 6. You will pick, and when you have 6 chocolates in front of you, you end up picking 1 chocolate. So Bharat wins and all the 4 participants get an opportunity to pick up chocolates. How many chocolates did George pick up? It has to be 1. Simply. Next, if we define a term opportunities of a participant as the number of cases for the number of chocolates that can be kept on table so that the participant is assured of victory. How many opportunities does George have? George is winning in how many cases? He's winning in 2 cases, when it is 5 and when it is 11. So how many opportunities does George have? It will be 2. If Bill wins, how many chocolates does Donald pick up the first time? Okay. If Bill wins, so we're looking at this case and we are looking at this case. And the fact that it is a theta question has to be a unique answer. I don't even have to look at the 12th case. How many chocolates is Donald picking up? 1. So answer here has to be 1. And this set is done. This set is beautiful. This set is difficult to comprehend, but this set is always going to be worked around. What would you do in that situation? Bharat's decision making we don't really care for, because Bharat's decision making is already aimed by Donald's decision making, or George's decision making is aimed by Bharat's decision making. So you can work your way backwards, and this is entirely about understanding. I don't know how helpful the video will be for this, but even if it is not, I would recommend please spend some time on this and think how your behavior, whatever decision you make, how that is going to impact the subsequent person. And probably if you haven't done coin picking as a separate topic altogether, first do that and then pick this up. It would be amazingly nice for you to comprehend. That will be all, people. Okay, bye. I hope you liked episode 1. There will be more episodes coming up in future. Okay, bye.